Hello. Uh, Thank you for giving me this opportunity to speak here. And I want to say a couple of things. First is that when I had approached Parvez for this lecture, he wanted me to keep it very elementary. But, at least the live audience are very distinguished. So, I've prepared this lecture. Hopefully there are some young people watching it online, and so I'll keep it elementary. So, please keep your expectations low. Okay, so this lecture is mostly about the Newton-Raphson method. And then we would look at three applications of it, all right? One is a very practical one, and two are historic. Okay, so let's start with the first application, and let's think about a problem. So the question is how to divide. How to divide, right? And when you learn how to divide, what that means is you learn it in terms of the other operations that you know how to do. So let's say you learned addition, multiplication, and subtraction, and now you want to learn how to divide, right? So it should not be in terms of division. So one way is to actually teach people what is called the division algorithm, right? But we're going to take a different approach. So typically when you have a question, you try to solve a simpler problem, if you can't solve the original problem. But in some cases, it's better to try to solve an even harder problem, okay? So I'm going to try to solve a harder problem. And the way I'm going to do that is, well, let's first simplify the problem. What does it mean to divide? You're given two numbers, let's say B and A, and you want to calculate B over A, right? Okay, but B over A is just B times 1 over A, okay? So now if you know how to multiply, right, then all you need to do is to find the multiplicative inverse of A. So, without loss of generality, you can assume that B is 1, okay? So now our question is simple, is given A, compute 1 over A, all right? And of course you want A to be non-zero, and you can also assume that A is positive, because if it's negative, then you can just put a minus sign in front of it, and it's a simple problem. So this is the question. So instead of finding the inverse, I'm going to solve a harder question, which is solve an equation. Solve this equation, 1 over x minus A is equal to 0. Okay? And, simple algebra tells you that, take A on the other side, inverse on the other side, the only solution is x equals 1 over A. So from a simple question, we've made this very complicated, right? So let's make it a slightly more complicated also. Well, why solve just this equation? Why not solve, even harder equation, a larger class of equation? So now we have a question which is solve f of x is equal to 0, where f is a general function, right? So now I will give you a general function, and you try to solve this equation. And we're going to approach this problem numerically, right? So let's start with this, and let's draw a picture. And so here we have, let's say, the coordinate system. Here you have some kind of a function, f of x, okay? And here, this is what is called the root, right, where the function becomes 0. And this is the value that we're looking for, right? Okay, so this is the point where f of x equals 0. Okay, all right, so here is one idea, and it's a very simple idea, is if you don't know how to solve this equation, take a guess. right? Take some kind of a guess. It could be an intelligent guess, and how to do that, we can discuss that later. And let's say this guess, you call this x0, right? Now this function is not 0 at x0, all right? So you want to know where to move, whether to move left or right and by how much. A way that can guide you is you compute the value of this function, and now you follow this tangent line, tangent to this point, okay? And here you will get x1, right? Okay, so somehow this tangent guided you in the right direction, not only in what direction to go, but by how much to go. All right? Another way of viewing this thing is that you pretended that the function was linear. It was a linear function. So if the function would have been linear, it would have really gotten you to the right point. So you started with a guess and you have somehow improved it, right? And that's beautiful because now you can repeat. Okay, now you can say that my guess is x1, okay, and I will use the tangent here to come even closer to the root. Okay, and then you can repeat again. You can say that I will take one more step, like that. And then it becomes very, very close, right? Okay, so you have this sequence, right? x0, x1, x2, and you can stop. And, there are many questions, when do we stop, and so on and so forth. But the guesses keep improving, right? And after a while, what happens is you're so close to the guess that if you're, say, computing on a calculator, all the digits are now correct. And, your accuracy is as much as your device or your capability allows you. So you can stop. So this method is called Newton's method, right? So what we want to do is understand how did we calculate this x1. If we do that, then it will give us a nice iterative way of improving our guess. Okay, so let's do that. So I want to see how to calculate x1 from x0. Now there's a wonderful method in mathematics and physics and all of science is if you can measure the same quantity in two different ways, right, then you can put an equation. Then you can put an equal sign and an equation has information. Okay, so I'm going to calculate one thing in two ways, all right, and that is the slope of this green line. Okay, the slope of this green line. So the slope, okay, this is where I have to use 12th grade mathematics. It has a name, okay? It's called the derivative, right? And there are ways of computing it. So the slope at this point is f prime of x0, right? So that's one way of calculating the slope. Another way of calculating the slope is, just by the very definition of it, it's rise over run. So my rise here is, this point is x0, f of x0, okay. So my rise here is f of x0, and what's my run here? It's x0 minus x1. Right? Okay. All right. So now I have this wonderful equation because I've measured the same quantity twice. So f of x0 over x0 minus x1. Have I done this correctly? I hope I have. So I'm going to divide. Yeah, let's do it this way. x0 minus x1 is equal to f of x0 over f prime of x0, and now I have, okay, I have to take this to that side and this here. So what would I get? Have I done this correctly? Is my algebra correct? Okay. All right, so let's write down that result here. Here, we are computing x1 as x naught minus f of x naught over f prime of x naught. Okay? And this is the equation I wanted. From the first guess, I can compute the function at the guess and its derivative, its slope. If I can do that, I get the next guess. And now this is purely algebraic. Okay? And of course, how do I compute x2? Well, you know, the indices just go. So x2 is just replace x0 with x1. Okay? And so on, right? Okay? So this is called Newton's method. Okay, or Newton-Raphson method. Now, you know, it's people think it's a very advanced method. It's just, you know, 12th grade mathematics. You can derive it from 12th grade mathematics. Okay, so what have we accomplished? And I will first show you an application and tell you how deep of a consequence it has. Okay, so we started by trying to divide without dividing. And for that, we were trying to solve an equation, which was a particular equation. Let's apply our method to that. Okay. So, f of x, in our case of interest, was this, right? So, to find Newton iteration, I have to compute its derivative, okay? And the derivative of this, if you know it, then, you know, I'll just write it and you'll believe me. If you don't know it, you know, just believe me, okay? Because I had said in the abstract that this was a prerequisite, right? So this is minus 1 over x squared, okay? Those who know a little bit of calculus would know that that's the derivative, okay? So now let's apply it. So x1 is going to be x0 minus f of x0. So that is 1 over x0 minus a, right, divided by minus 1 over x0 squared. Okay, let's do a little bit of algebra. Okay, you wouldn't mind that. And this is going to be x0. And this, I reverse it and multiply it. So this is plus 1 over x0 minus a times x0 squared. And this, when it's multiplied here, gives me an x0. And this one gives me minus a x0 squared. And I can simplify this as 2x0 minus a x0 squared. If you want, you can write it as x0 minus 2a x0. This is fine, whatever you prefer. Okay, why is this so beautiful? This is spectacular. You know, we've done something amazing. No divisions. We can do this iteration with the operations that we already know. We know how to add, we know how to multiply. Okay, we know how to subtract. All right, so we've learned how to divide without dividing. You know, that's the real beauty of this thing, that we have.
Not exact.
Huh?
Not exact.
Yeah, it's an approximation. All right, so now I'm going to come to applications. All right, so you all have computers and calculators, right? So there are two kinds of numbers that you have there. One are integers, you know. When you multiply, things are exact and add and subtract. The other are called floating point numbers, right? Where you have a certain decimal place accuracy, right? You don't have exact numbers over there. When you multiply, you don't get actually the product of two numbers. You get it to a certain decimal place accuracy. So this method, once you get to that accuracy, you can actually stop. All right? Okay. So let's ask, so your question is very interesting. Let's ask one very interesting question. So the question is, how good is this? Let me write down this iteration. What was it? 2x. That was the iteration, right? We found. Okay. So how do we measure error? All right. So, let me say something very elementary. There are two ways of measuring errors, right? One is relative error and the other is called absolute error. Okay. So for example, if I tell you the radius of the Earth to within 1 meter accuracy, you should be impressed, right? But if I tell you the height of Sohail within 1 meter accuracy, that's not very impressive, right? Okay. So let's try to compute the relative error. Okay. So in this case, what is the correct answer? Okay. So that is 1 over a, right? What is our answer? Well, initially it's this. Okay. But this is absolute error, right? If, there's a signed absolute error. Okay. So what would be relative error as I divided by the answer, right? That would tell me the relative error. Okay. And this is, let's call this E0. Okay. And this thing is, when this thing comes here, the 1 minus ax. Okay. Or shall I do the algebra? It's all right? Okay. All right. So this is actually the absolute value of this would be the error, but we'll right now let it be signed. So if we had the perfect answer, the product of these would have been 1. And this is seeing, well, how far off is the product from that 1? So it has a nice interpretation, right? Typically, relative error doesn't have another interpretation, but in this case, it does. Okay, so that's the relative error. Now, when I see this relative error, I have this internal urge to square it. Do you have it? Who has the urge to square it? Other than me? Okay. All right. So let me go ahead and square it. Is going to be 1 minus ax naught whole squared. And this I remember from my algebra days, right? This is first term squared minus 2 times first term into second term plus second term squared, right? A squared x naught squared. Okay? And this I can write as 1 minus, let me take out an a. So this is 2x naught minus ax naught squared, right? Do you notice something?
Yes, x1.
This is x1, so this is 1 minus a x1. Okay? So, just follow your urges, right? Especially if they are about squaring and ice creams. Okay? So this is the second error. So the second error is going to be the square of the first error. Or in this case, the first error is going to be the square of the 0th error. So as long as your original relative error was less than 1, you're fine. Okay? This thing is going to converge quadratically. Okay? All right. So with this iteration, let's say you had 1 decimal place accuracy to begin with, right? Then when you do 1 iteration, you'll have 2 decimal place accuracy, right? So it's going to go like, let's just call this epsilon. It's going to go epsilon squared. And then the next error is going to be square of this, which is 4. And next error is 8. And next error is 16. And next error is 32. So you will double your accuracy every time. the number of digits. Okay, so this will very quickly converge to the right answer. Okay, so typically in a computer you have 64-bit accuracy or 128-bit accuracy. Few iterations will get you there. Now, the thing is, I'm not sure about the very, very modern computers, but about 20 years ago, this method was what was used inside a computer. Yes? No, okay. All right, so, I mean, this 10th grade level mathematics is what is used in a computer, in every computer to divide. Okay, some of you people have studied computer hardware, right? They teach you how to make adders, they teach you how to make multipliers, but they never teach you how to make dividers. Okay, and they never teach you how to make subtractors either. Why don't they do that?
Because you can do subtraction with an adder. You just need a negative input.
Yeah, you're right.
You can do subtraction using an adder. You don't need a separate subtractor because subtraction is the inverse operation of addition.
And that's why the 2's complement notation has been invented. Yeah. So we don't need that. So this is a wonderful application, right? A very simple thing, and you've learned how to divide without dividing. Okay, so now let me apply this to another function. Okay. So the second function that I'm going to apply this to, okay, if you look at the ancients, right, ancient mathematicians, there seem to be some obsessions, okay? And one of the obsessions is about calculating square roots, okay? And I think there's a very good reason why people want to calculate square roots, and they don't really care about cube roots or things like that. And the reason is the Pythagorean theorem. You want to compute distances and you have to compute square roots. Even in 3 dimensions, you don't need cube roots. You need square roots, right? So it's extremely important. So now the problem is you're given a number n and you want to calculate square root of n. Okay? And we use the same trick. We take the function f of x equals x squared minus n, right? And we find a positive 0 of it. Now, if you solve f of x equals 0, right, then x squared equals square root of n. These are the only 2 solutions. So, you just find one positive one, you have the other. So, once again, what we can do is we can apply Newton's method to this and see what we get. Okay, so let's do that. Okay, so I forgot what was Newton's method. It was that the next guess is the previous guess times the function value over the derivative. Okay, so might as well compute the derivative of this function also, which again, if you know a bit of calculus, it's this. If not, just believe me. Okay. All right, and now let's do this. x1 is going to be x0 minus x0 squared minus n over 2x0. Okay? Sorry. And I can just stop here and just right here I can ask, why is this beautiful?
No square roots.
That's it. We've solved the problem. We knew how to add, multiply, and we've learned how to divide. So, we can now compute square roots. Same idea, same method. Okay? So let's just do a little bit of manipulation here. And this is, this would be, right? Please check me because I tend to make a lot of algebraic mistakes. Right? So this is 2 x naught. Oh, the 2 goes away. X naught. And I'm going to write this slightly differently. I'm going to take out the half here. And what would I get for this? Is x naught, right? And what would I get for this? Is n over x naught. Okay, and I'm going to talk about these 2 equations. This one, and I'm going to talk about this equation. Okay, so now we are going to come to the Bakhshali manuscript, right? And the Bakhshali manuscript is one of the most important manuscripts in the history of mathematics. Okay, and it was found near Peshawar in a town called, in a village, or probably it's now a town called Bakhshali. And why it's significant, it has a very clear use of 0, right? So we know that 0 was invented and perfected by the time the Bakhshali manuscript was written. We of course can't say that was the time, it could have been earlier. But we know that 0 was developed before the Bakhshali manuscript. So it's a very important flag post in the history of mathematics. And it has a lot of calculations. And what they're doing is they're computing square roots. And they're computing square roots of non-square numbers. Right? So they're trying to get as many decimal places right. Okay, it's a fascinating manuscript, and it's so sad that our young kids don't know about it. We should be studying it. We should be doing research on it. There should be a lesson in our course books about the Bakhshali manuscript, right? Because it's our heritage. So that's what they're doing.
Which civilization?
Huh?
Where precisely?
It's it's near Peshawar. Yeah, near Peshawar. Yeah.
Town called Bakhshali.
Yeah.
Which civilization is it from?
So it's 300 years Common Era, right? So it's not the Indus Valley civilization. It's after that. So probably.
Which civilization was in?
Probably the Buddhist period.
I see.
Yeah. But our, over here, the Indian subcontinent, right? But the Indus Valley civilization sort of had declined by that time. So there's the Aryan migration theory, right? There's the Aryan invasion theory, Aryan migration theory. So it's after the Aryans had, I think, arrived, yeah.
Yeah, but there is confusion about the exact date. Some say it's 3rd century and some say it's about 6th century or
6th century
AD.
AD.
Yeah.
Definitely should be earlier. Where it comes from is it's essentially making a diagram of the abacus. The number of beads that you have, one line, and then the next is when all of those are filled, then go here. So that's when it comes to 10, then you go to the next. So then when you just turn it around like that, which is the way the Japanese have their abacus, then if there's nothing in one, you want to just denote that, where you're denoting over here how many by just the number of pieces, then that was a dot. Nothing in that row. And that's where it came from. And the Japanese and the Chinese continued with physical abacus. But over here, well before the 5th century AD, this had been arrived at, the use of just the diagram.
No, but actually this manuscript is very long and people said some
Yeah,
parts
yeah,
are
there's
from
much
the
more in it.
3rd century and some parts from the 5th and even
I
from
can see you
maybe
saying not
maybe
just the
from the
zero.
9th or 10th century also. So
नहीं पहले वो तो क्योंकि algebra भी उससे पहले आ गया ना.
yeah,
This is all there before the fractions etc. before.
So, archaeology and history of mathematics are extremely vibrant fields. And every time I go and look at stuff there, I realize that knowledge has changed. So, exact dates and all that, but it just is that this method is being used in the Bakhshali manuscript to compute square roots. Okay, now this thing, let's look at this equation. All right, this has a very nice,
But these people didn't have calculus, so how did they compute derivatives? How were they computing derivatives?
Okay, so the thing is, we know that they were doing this iteration. We have no idea how they got it. Okay, so they just knew that. So, for example, the Bakhshali manuscript doesn't say why the method works. Proofs don't enter into mathematics till the Euclid's era, right? Okay, so they just were computing this and the right answers were coming. Let me get to this and then I'll give you an argument why they may have reached here. Okay, this was just a little bit of algebra, and this is an iteration which was used by the Babylonians, okay, the Greeks and the Indians. Right, so they were using this iteration. It's far easier to understand how you will come to this, okay? How you will get to this point. Let me do that for you. Okay. So suppose if you have a guess, G, and you want to calculate square root of n, all right? Now, let's take two cases. Suppose the guess is less than the square root of n, right? Then what can you tell me about n over your guess? So I have n and I'm going to divide it with a quantity which is strictly less than the square root of n.
Would be greater than g, greater than g.
Greater than square root of n. Right? Agreed? So I have a guess which is less than square root of n. If I divide n by some quantity less than square root of n, what will be left over would be greater than square root of n. Okay. On the other hand, if I have a guess which is greater than square root of n, okay, what would n over g be? Less than square root of n. Okay, so if you look at the picture, there is somewhere square root of n here, and I realize that the guess and n over the guess are on opposite sides of it. In this case, they are on opposite sides of it, and in this case, they are on opposite sides of it. Okay, all right? Okay, so I know that my answer is between the guess and n over the guess, right? So what I do is I take the arithmetic mean, and that's my new guess. Okay, so you know I didn't do any Newton's method or anything like that. This could be you could arrive on this just when you're playing with this thing, right? So look at the argument. It's lovely when either this and it works, either that it works. If the guess is smaller than your answer, then n over guess must be larger than your answer. If the guess is larger than your answer, then n over guess must be smaller than your answer. That means the guess and n over guess is, bound your answer. So let's take the arithmetic mean of that. That will be somewhere here, and that will be a better guess. Okay, and keep doing that, right? It's really beautiful. Okay, all right. Another thing is, another way of seeing this is, that if you look at x, and if you look at n over x, then what is their geometric mean? Square root of n, right? So you want to compute the geometric mean of these two quantities. And here you're saying, I don't know how to compute the geometric mean because I have no idea how to compute square roots. So let me just approximate it by the arithmetic mean. Okay, so that's another way of maybe arguing that this method will converge.
However, they are doing the division operation, n over g.
Well, I think long division.
Long division.
Long division.
Properly dividing.
Yeah, obviously, after certain numbers of accuracy, they'd stop. You know, just like kids, we used to stop when, you know, we were given some problem, you know, teachers कहते कि 3 decimal के बाद छोड़ दें, right? So that they were doing something like that. Yeah. So you know, it's lovely that. Okay, and the interesting thing is that the modern Newton method was not actually discovered by Newton. You know, he only stated it for polynomials, and you know, it was very complicated what he was doing. It was, so you know, sometimes when you're such a huge person, you know, many things are credited to you. Okay. So this was all that I was supposed to cover, but how much time do I have? I have a little bit of time. So I'll say a couple more things and then maybe I'll do one thing extra. Okay.
Babylonian mathematics.
This is Babylonian. This is Bakhshali.
Aren't they the same?
They are the same, yeah.
Achha,
They are the same, but Bakhshalis were squaring things and adding and then doing all of this. And Babylonian had done the algebra for this. Yeah.
Excuse me, I got a question. Imagine that I have got funding from government of Pakistan that Bakhshali proved that our heritage is very, very rich. So I have seen that from Bakhshali manuscript we can reach somehow to Newton-Raphson method. So I can prove by some proof that since from Bakhshali manuscript, as you have mentioned, we can reach Newton-Raphson method. Therefore, historically, Newton-Raphson method was not by Newton and company, but rather this was by the Bakhshali.
Yeah, the only thing is somebody will say Babylonians were before Bakhshali. That'll be the end of that argument.
Thank you.
Yeah.
Newton's method was more general than what the Bakhshali was.
Yeah, Newton's method is far more general, right? Okay, so I want to just talk a couple of things. So it turns out that you can apply Newton's method to complex variables, all right? And it's very interesting if you apply it to this function z cubed minus 1, okay? So if you want to solve this z cubed minus 1 equals 0, then let's draw the complex plane, right? And this is the unit circle. One solution would be here, another solution would be here, and the third one would be here. If you guys don't know this, you know, and you're lost, you can snooze for a little while, okay? All right, now here's something interesting that happens. Suppose if I take a guess here and I apply Newton's method, it goes and converges here, right, to this root. If I take a guess here, it goes and converges there. And if I take a guess here, it goes and converges there, right? That's sort of obvious. So, you know, you have, if I can do this right. So you sort of have these things converging here, all right, and these things converging here, and these things converging here, right? What is interesting is what will happen when I go near these lines. You know, somehow these roots are attracting it equally. And what you can do is you can go to every point, apply Newton's method, color it red if it converges there, color it yellow, and color it white, depending on what root it converges, and black if it doesn't converge, right? So what you get is a fantastic, fractal, okay? You get this beautiful fractal, right? So One way to get to fractals is just study Newton's method using on complex numbers. Okay, so there's that thing. So just studying Newton's method can lead you to dynamical systems, to many subjects. This is one simple thing. Okay, so since I have time, I'm going to do one more small thing. Okay, and I will then end there and we can have a discussion. Okay, so here's another method that I'm going to talk about. So remember how we got Newton's method? We took a function and we had one guess, all right, that we called x0. In this method, suppose we cannot compute the derivative of the function. It's too complicated. Then what you can do is you can take two guesses, and rather than drawing the tangent, okay, you can draw the secant, and you get the next iterate, right? Okay. So another way of thinking about it is our iteration was x1 is equal to x0 minus f of x0 over f prime of x0, right? So now I don't know how to compute this function, this derivative, so I do a linear approximation of it. Okay, so what I will get is this would be x0 minus f of x0 times this I will approximate by f of, is that right? Okay. All right. Okay. And so I will call this the second guess, right? And then now I can do a little bit of algebra over here. Okay. This thing is called the secant method. Okay. All right. And if you do the if you apply it to this function 1 over x minus a, then you get an iteration which is something like x2 is equal to, what did we have, 2x0, right?
2x0 minus a x0.
Yeah, so you get x1 plus x0 minus a x1 x0. You get some iteration like that. Okay, and the reason I'm not doing the algebra is because I want to leave that as an exercise for you. And what you can do is you can do the similar error analysis that we did. Okay, and you get this lovely equation, which is that the first one, let's say the error is epsilon, so you get epsilon 2 is the product of the previous two errors. Okay, rather than, in the Newton's method we got a square, so here you have the product of the previous two errors. So initially if you had accuracy of epsilon, and then epsilon, let's say both were nearly the same, the next one would be what? Just the product of these two, so it'll be, right? What would be the next one? And the next one?
5.
And the next one? And the next one? So Fibonacci strike again, all right? So, the error goes on as Fibonacci numbers. And so this analysis that I'm doing, this analysis, I've done it for a particular function, all right? But if you know something called Taylor's theorem, which all of you do, but I'm not allowed to, write it down because it's supposed to be too difficult. If you use Taylor's theorem, then you can prove this, the convergence of Newton's method is quadratic for all reasonably well-behaved function. Where reasonably well-behaved would be some kind of technical conditions on the derivative and the second derivative and their bounds on them. And you can prove the same thing for the secant method, that the convergence is Fibonacci-ish for all reasonably well-behaved functions. Okay, and then one of my friends had suggested that when I talk about this thing, I should also talk about machine learning.
What's it talk about?
Machine learning, AI,
Machine learning.
okay, gradient descent, and all that things. So essentially, these optimization methods, Newton's method and secant method, are extremely important over there because when you are trying to optimize a function, you want to set the derivative equal to 0. So essentially, you are applying these methods to the derivative, right? Over there, things are slightly different because you have a vector-valued function and so on and so forth, right? But so I'm a big fan of basics first. If you want to understand something, if you want to understand gradient descent or machine learning or whatever, please first learn the Newton's method, Newton-Raphson method, and understand what it exactly is doing. So shall we stop here? Yeah, so my 1 hour is gone, so let's stop. Thank you.
I was thinking that it may be worth pointing out why people might have been avoiding doing division when it's so easy to do division. And the point, of course, is try doing division with the Roman numerals.
Yes, absolutely.
Try doing multiplication, you just about make it. Try doing division, and that is what was being used. The development, what I was thinking of was more that in the further eastern part of India, the zero had been developed, and then numerals got developed from there. So the procedure of division was developed in another way. This now I just connected, that this is obviously doing other things. Like when I was asked, have I divided without dividing? And my immediate reaction was, well, of course, I'd do it geometrically. That's the way the Greeks actually did it, to the extent that divide by 2, then divide by 2, then divide by 2, and if this has gone too low, then go between and get the correct answer.
Yeah. Sorry, I should have mentioned this. A far more basic method for computing roots of a function is called bisection method, right? So if you have a function and it's continuous, and you can find 2 points where it's positive on one side and negative on the other side, then the midpoint is a test point, all right? And then you can close in on it. In that, what happens is, with every iteration, you get 1 extra bit of accuracy. So it converges linearly, okay? But it is the safest method. It's the safest method because once you have got a function which is positive here and negative here, the only thing that can mess you up is discontinuity,
Of course, where Newton's method goes wrong is when you've got the slope going nearly 0.
Yeah.
So there,
if there's a double root, you're in trouble.
Yeah. Well, what you can do is go to the next order and put it into the square root, and now you won't have a problem.
Yeah.
So unless it goes even further closer to 0. But I developed that for myself. These things automatically come out that when you try using the bisection method, first it seems easy. And then you look at the values and you say, what the hell, I know this is so much more, it's nearly there already, so let me keep a lot more of this, a lot less of this part and a lot more of that, and then it'll come out. And that's the Newton method.
Yeah, so here's another method which is used, which gives you the best of both worlds, is you have an x1 here, and you have a x naught here, and you have a x1 on the other side, right? But now you use the secant method to get a new guess, all right? But you discard the point that makes sure like that.
Yeah.
So you get the convergence of the secant method, but the robustness of bisection
Yeah,
method.
it's better.
Yeah, but I want to make a point is, to me, all these variations, you can spend a lifetime working on them. To me, what is really, really important is the seedling, is the germinal. Once you understand the basics, then you can go and look at all the issues that Asghar is pointing out to.
Yes, it's actually when one tries doing the calculations on one's own,
Yeah.
you learn about these, and you learn to do that intuitively anyhow. The basic bisection method, the Newton method, and when you try to go beyond, like with the secant, it doesn't seem worthwhile. When I'm using a calculator and just doing it by hand, the Newton method is the easiest to apply.
Newton's method has two setbacks, right? Let's look at the iterations of Newton and secant. And this is something that I always make sure my numerical analysis class understands. So Newton's iteration is x1 is equal to x naught minus f of x naught over f prime of x naught. And let's say that its convergence is quadratic. So epsilon 1 is epsilon 0 squared, right? Okay. In one step, you reduce, you get quadratic convergence. But what is the cost? The cost is two function evaluations. Actually, a function evaluation and a derivative. Typically, the derivative is harder to evaluate than the function because of the chain rule, product rule, blah, 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 right? So this is two function evaluation. Whereas bisection method, secant method is only one function evaluation, all right? And its convergence is, this to the phi, where phi is the golden ratio because of those Fibonacci numbers, right? But so here you have one function evaluation giving you this, there you have two. So you'd rather use secant method. Okay, so, because you can do two steps of the secant method at the cost of one step.
Yeah, you have to go, if I'm not doing it on a computer and I'm just doing the thing myself by hand, and I have to do more things in working out than it's worthwhile. So I just go with which I did. I went with the Newton method just by hand, get the very quick answers. And it really goes easily.
I think the third one method is very quick. Such both of this method that is this is secant method, and first one was Newton-Raphson method. Third one, bisection method. I think this is
bisection method is just for bisection method. All you can say is epsilon 1 is equal to epsilon naught over 2.
yes.
Okay, so let's say that you have 5 bits of accuracy. Bisection method will give you 6 bit. Okay, Newton's method will give you from 5 bits to 10 bits in one shot.
Okay.
So Newton's method is far, far superior, right? This secant method will give you from 5 bits to 5 to the power 1.6 bits, whatever that turns out to be, but with only one function evaluation. So you could actually do 2 secant method steps and beat Newton's method.
Okay, so it's very beautiful that from Newton-Raphson we can have the simplest one, which is bisection, and then best of the two words can be found using secant. But if I have even faster convergence than the Newton-Raphson, whether there is some immediate improvement on the top of this Newton method?
You have an even faster So you're saying, is there a method you can invent that's better than this?
Any famous method which is better than Newton-Raphson in terms of convergence? And who was this Raphson guy, by the way? Thank you.
Well, I'm sure he was a mathematician. Okay. No, so you're saying, is there an even faster method? I think that probably the research is, in terms of single variable, it's probably very difficult that somebody will ever find something. People really are now looking at, multivariate functions, okay? Because, they're computing the derivative is not that easy. And the second derivative, it becomes, if you're in dimension D and all that, and convergence analysis in there, those are far more important problems rather than try to beat these methods. If you come up with a fundamental method which is even close to these, it would be very interesting, because even if it may not beat these, in higher dimensions it may be useful.
This method they call a graphical method, where they zoom in. They're actually, this Newton method working behind that.
Well, graphical method is for teaching, right? It's not for, isn't for calculations. I mean, how far you can zoom in, right?
Yeah,
Shall we end there? Any other questions?
Okay, another remark. So, I mean, in computer science, we try to find faster and faster way to divide the thing.
Mm-hmm.
And what happened that Intel, they come up with some crazy approximation division algorithm that they implemented on their chips, on Pentium chips, and then eventually it failed on some particular
The Pentium bug.
Yeah, the Pentium bug.
Yeah.
So
yeah.
do you have any idea about the Pentium bug? Algorithm was responsible for creating Pentium bug?
I don't know. I just remember there was big news and that Intel lost
$500 million.
$500 million,
Yes,
and
exactly.
which would be in today's money would be a lot more.
Yes.
Yeah. So, but somehow money doesn't sort of excite me that much. Either.
But
it's-
the
either
bad algorithm does
either
not
the
excite
making
you.
of it or losing of it. That's just I'm sort of, I say, okay, somebody lost 5 billion. They must be very rich. That's my attitude.
But I'm not focusing on money. I'm talking about the deception of the algorithm that seems very reasonable to Intel guys and other people, so that they implement it in a hardware. But the algorithm is not behaving well on some particular values, and it is creating errors.
See, numerical methods and numerical analysis is sort of like a black art. That's what I think about it. You learn all these methods, and when you have a real life problem, none of them work. Okay? Because there's this interplay of round-off errors with truncation errors. All right? And sometimes you're concentrating on one kind of error, but the real problem is another kind of error. So, I haven't really done numerical computing practically, other than for teaching purposes. Mm-hmm. So those questions, why these algorithms fail, would be somebody expert, some expert would be able to tell.
Right. Thank you so much.
Interesting that you mentioned the Bakhshali Manuscript, and I had a similar question. So I was reading about the cuneiform tablets that they used to have in ancient Sumeria, and they would use these stone clay tokens for trading to denote the amount of quantity of any material that they're trading. And people have speculated, I might be wrong, but this is originally what led to the invention of written numerals around 4,500 years ago in the ancient Sumerian period. So my question to you is, do you think that it was did mathematics initially evolve from this kind of an applied context where it's being used for things like trade in the real world, or was it more of an abstract context the way the ancient Greeks had with their, like Platonic solids and shapes and geometry doesn't exist in the real world, it's an abstraction. So which one of these two streams would you say was more like fundamental in the ancient mathematical world which led us to where we are today?
Well, I can tell you what I think. I think that practical problems would have been far more important in the early development of mathematics. The abstraction is going to be an afterthought. You have to first learn how to count up to 500 or something, or 20 or 30, because those are the number of animals you could keep or whatever, before you realize that, oh, the number of integers is infinite. There is no observable example of anything that is infinite. So I think practical reasons, trade, keeping track of just things.
Also astronomy and keeping track of the weather for like crop cycles,
Yes.
that also led to.
Yeah, time, developing calendars because you're an agricultural society. These early mathematics had to do with that. I mean, I think Greeks were spectacular. I mean, Euclid was amazing. The kind of abstraction and kind of love for proofs that he had, it's just at another level, So that's what my take is. On the other hand, let me tell you that history of mathematics and archaeology are such vibrant and fast-moving fields that I get scared when I'm asked to comment about it. There's a discovery recently, I didn't even know about it, in Turkey, Göbekli Tepe. It's something like 10,000 years old, or 11,000 years old. Okay, so this data is coming, and it was there are like 3 accidents that led to the discovery of this site. So what's out there in archaeology, we don't even know, right? With these sites coming up, there is a site of Indus Valley civilization which may be bigger than Mohenjo-daro. Okay, so I really feel very scared when people ask me about history, yeah, because I don't read it actively.
Okay, so like there is some sort of beautiful thing or something which is there in the nature or written in some book. So we discover those facts from different methods. Like you discovered this dividing by dividing without dividing, and then that is connected somewhat with the Newton-Raphson method. So my question is whether it is possible that there are some facts and people looking from those facts from geometrical perspective they see it differently, from algebraic perspective they see it differently. Example is this Pythagoras theorem. People have seen it differently and then they proved it in 10 different ways. Thank you.
Yeah, look, I mean, physicists will tell you, right, that even Newtonian mechanics, there are 3 or 4 different approaches to it, right? There's the Lagrangian, the Hamilton, and and each one of them gives you different insights. And for different problems, one approach may actually give you a very transparent solution, very easy to understand one. The other one may give you very obscure things. So I have seen that kind of mathematics where there are several proofs available, all right, but each one of the proofs actually gives you insight, a different kind of insight on the problem, and some of them don't at all. There's just, you might as well memorize them. They're like black magic, right? So yeah.
But ultimately, all the best proofs are written already in the book.
Yes.
And mathematicians only find things.
Unfortunately, the book is with the supreme fascist.
Would you please recommend some other books on such beautiful topics? Not
So
only the.
I have given you a list of 3 articles which will be placed on the Facebook page. One is on the Bakhshali Manuscript, and one is on I think this Babylonian mathematics. And I may add some more, and when on the Facebook page I'll put some more links. Okay, there are the 3 links there. Okay, thank you so much.